Number one, assume that females have pulse rates that are normally distributed, the mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. If one adult female is randomly selected, find the probability that her pulse rate is less than 81 beats per minute. Do we need to use the central limit theorem, or do we use our regular normal distribution? We can just use our regular normal distribution because we know that this is normally distributed. Females have pulse rates that are normally distributed. And I'm only picking one. Stat, normal. And my standard deviation is 12.5. And I want to find the probability that her pulse rate is less than 81 beats per minute. I hit compute. We want this to 4 decimal. 1, 2, 3, 4. The next one is a 6. I'm going to round up. If 4 adult females are randomly selected, find the probability they have a pulse rate with a mean less than 81 beats per minute. I need my standard deviation, which is equal to my standard deviation divided by the square root of n. And here my sample size is 4. I can use it because I already know that pulse rates are normally distributed. This is going to equal 12.5 divided by the square root of 4. I have 4 adult females, which is 6.25. To 6.25. Everything else is going to stay the same. And I hit compute. The interpretation. Why can the normal distribution be used in part B, even though the sample size does not exceed 30? Since the distribution is of individuals, not sample means, the distribution is a normal distribution for any sample size. For A, that's true, but for B, no. Since the distribution is of sample means, that's true, not individuals, the distribution is a normal distribution for any size sample. Since the mean pulse rate exceeds 30, nope, has nothing to do with the mean pulse rate. Since the original population has a normal distribution, the distribution of sample means is a normal distribution for any size sample. That is number one. Because the original population of females was normally distributed, I can use the central limit theorem. Number 2, the weight of a certain brand of candies are normally distributed with a mean of 0.8586 and a standard deviation of 0.512. A sample of these candies came from the package containing 470 candies, and the package label stated that the net weight is 401.1 grams. If every package has 470 candies, the mean weight of the candies must exceed this value for the net contents to weigh at least 401.1 grams. First, if one candy is randomly selected, find the probability that it weighs more than 0.8533. I'm only picking one. This is an individual. I don't use the central limit theorem. I don't have to divide by the square root of n. And even if I did, it would just be dividing by 1. I want it to weigh more than 8533. I compute. The next number is a 2, so I don't round up. Check answer. If 470 candies are randomly selected, find the probability that their mean weight is at least 0.8533. The only thing that's different is my standard deviation when I'm looking at a sample size is going to be the original standard deviation divided by the square root of n, and here n is 4. My standard deviation is 0.00236.168. And we still want to know the probability that it's greater than 0.8533. Yes. and we get pretty significant number. That last number is gonna have to go up 1. You need to interpret it. Given these results, does it seem that the candy company is providing consumers with the amount claimed on the label? Yes, because the probability of getting a sample mean of 0.8533 or greater when 470 candies are selected is not exceptionally small. The probability is very big. It's almost 100% probability. We should be getting what we pay for, and that concludes section 6-4. Thanks for watching.